Ever hit send and just stop to think about what actually happens? I mean, how do your words, or a photo, or even a video just zap across the globe in basically an instant? Well, today, that's exactly what we're going to do. We're going to follow a single bit of data on its absolutely incredible high-speed journey. It really all comes down to this one question, right? How does a thought, something you type into your phone right here, end up on a screen thousands of miles away over there? It feels like magic, but I promise you what's happening behind that screen is one of the most amazing feats of modern engineering. So our journey kicks off the second you create that piece of information. Before it can go anywhere, it has to be translated into a language that machines can understand, and more importantly, a language they can send reliably. And that's where we meet our hero, the digital signal. See, back in the day, everything was analog. Think of these continuous waves, kind of like the sound of your voice traveling through the air. But here's the catch. They get messy. They pick up noise. They get weaker over distance. Digital signals, on the other hand, are a game changer. They turn everything into a clean, simple series of ones and zeros. This binary language is what makes our modern world, well, work. And this right here, this is the digital signal's superpower. Look, the original, perfect signal, it gets all distorted by electrical noise during its trip. But here's the magic trick. Because the information is just ones and zeros, the gear along the way can easily tell the difference between the signal and the noise, and it can rebuild a perfect, clean copy. It basically heals itself. That's why digital communication is so incredibly reliable. So how does this all fit together? Well, this diagram is going to be our map for the whole trip. I know, it looks a little complicated, but don't worry. We're going to walk through the most important parts one by one. We're going to follow our message all the way from the source on the left, through all the packing and protecting, and right to its destination on the other side. Okay, our first big stop on the map is packing the data. Before our message can even think about leaving, it has to be packed up efficiently. I mean, you wouldn't take a giant, half-empty suitcase on a flight, right? Well, the exact same idea applies to our data. Now, the official term for this is source coding, but you know it by a much more common name, data compression. The goal here is really simple. How can we say the same thing but with fewer bits? It's all about making our data package as small and as lightweight as possible so it can travel fast. And why does this matter? Oh, it matters a lot. Without compression, streaming your favorite show would be a total buffering nightmare. That high-res photo you want to send, it could take minutes instead of seconds. Compression is the unsung hero that saves bandwidth, storage, and time, making our digital lives possible. Now, there are basically two ways we can pack our data. For things like text files or computer programs, where every single letter and number has to be perfect, we use what's called lossless compression. It just finds smarter ways to represent the data. But for things like images, audio, and video, we can use lossy compression. This is where things get really clever, because it makes files way smaller by throwing out tiny bits of information our eyes and ears probably wouldn't even notice. I mean, just look at this. The original picture of the sunflower is 738 kilobytes, but after some smart lossy compression, we get it down to just 58 kilobytes. That's more than 90% smaller. Sure, it might lose an absolutely tiny bit of detail you'd never see, but that's a trade-off we're happy to make for a file that's so much easier to send and store. Okay, so our message is packed up nice and tight, but the journey ahead can be dangerous. We have to protect it from anyone trying to snoop on it, and we have to give it a way to fix itself if it gets damaged. This brings us to the next stage, security and self-repair. The first layer of defense is encryption. Think of this like putting your message in a locked safe that only the person you're sending it to has the key for. It scrambles the readable data into total gibberish, so even if somebody grabs it, they won't have a clue what it says. This is its digital armor. But what about random damage? What if some stray noise flips a 1 to a 0 by mistake? That's where channel coding comes in. This is like giving our message its very own first aid kit. By adding some clever extra bits, some redundant information, we give the receiver the power to spot errors and, in many cases, even fix them on the spot. So how on earth does that work? Well, here's a really simple way to think about it, called the repetition code. Let's say we want to send a 0. Instead of sending it just once, we send it 3 times. 0, 0, 0. Now, if noise flips one of those bits and the receiver gets 0, 1, 0, it just takes a majority vote. It sees 2 zeros and 1 1, so it knows the original message was almost certainly a 0. Pretty simple, but incredibly powerful. All right, our message is compressed, it's encrypted, and it's got its first aid kit. It is ready for the most dramatic part of its trip, launching into the world, whether that's through a fiber optic cable or just riding the open airwaves. Here's the thing, our digital ones and zeros can't really travel far on their own. They're like a surfer without a wave. They need to hitch a ride on a much bigger, more powerful, high-frequency wave to get anywhere. And this process of imprinting our data onto that powerful wave is called modulation. Okay, let's break it down. This wave right here, that's our data signal. It has all the information, but it just doesn't have the energy to go the distance. This is our passenger, waiting for a ride. And this powerful high-frequency wave, this is the vehicle. This is the express bus that has the juice to travel across the country or even around the planet. And boom, through modulation, our little data signal changes the shape of the big carrier wave, basically encoding itself onto it for the journey. The passenger is officially on the bus. The message is on its way, ready to travel at the speed of light. So after traveling through wires and air, maybe bouncing off a satellite, fighting through all kinds of noise, our message finally reaches its destination. The journey is almost over, but there are a few final, super important steps. You see, at the receiver's end, everything we just did happens in the perfect reverse order. First, it gets the message off the carrier wave. That's demodulation. Then it checks for any errors and fixes them. After that, it unlocks the message with the right key, decryption. And finally, it unpacks the file, decompression, until the original message is back, perfectly restored. But what's really going to blow your mind is that this whole journey we just followed for one single message, that's happening trillions and trillions of times every single second of every single day. Each little bit is zipping through this impossibly complex web, creating this invisible, instantaneous network that connects our entire planet. So the next time you tap send, just take a half second to appreciate the absolutely wild, high-speed, and resilient journey your message is about to take. It's a symphony of physics and engineering that weaves our world together. So, what message will you send next?